Welcome to Mathematical Analysis. Today we are going to explore two of the most foundational concepts in real analysis, the supremum and the infimum. If you have ever wondered how mathematicians handle boundaries for infinite collections of numbers, you are in the right place. We will build this from the ground up, starting with a simple analogy, moving into the formal mathematics, and finally seeing why these ideas are the absolute bedrock of calculus. Let us dive in. To understand these concepts, imagine you are standing in a room with a group of friends of different heights. If you want to build a flat roof over everyone's head, any roof that is taller than the tallest person is an upper bound. You could build it at 10 feet or 100 feet and it would work. But to save materials, you would build the roof exactly touching the top of the tallest person's head. This lowest possible roof is called the supremum. In mathematics, an upper bound is any number greater than or equal to all numbers in a set. The supremum is simply the tightest possible ceiling you can place over a set without crushing any numbers. Now that we understand the idea of a tight ceiling, let us look at how we write this using precise mathematical symbols. Let U be the supremum of a set S. For U to be the supremum, it must satisfy two strict conditions. First, every element X in the set must be less than or equal to U. This guarantees that U is a valid ceiling. Second, we must prove it is the lowest ceiling. If you decrease the variable U by even a microscopic amount epsilon, it physically breaks the ceiling. The new value, U minus epsilon, is no longer an upper bound, meaning at least one number X from the set will poke through and be strictly greater than it. This perfectly captures the idea of a least upper bound. The exact same logic we just used for the ceiling applies in the opposite direction for the bottom boundary of a set. Think about building a solid floor under everyone in that same room. Any level below the shortest person's feet is a lower bound, but the highest possible floor you can build that still stays under everyone is the infimum. Formally, a number is a lower bound if every single number inside the set is greater than or equal to it. Out of all the possible lower bounds you could pick, the largest or highest one is called the infimum, or the greatest lower bound. If you raise this floor by even the smallest fraction, it will crash into at least one number in the set. Just like the supremum, we can define the formal mathematical characterization for the infimum. Let W be the infimum of a set S. It must satisfy two conditions. First, every number X inside the set must be greater than or equal to W. This confirms that W is a valid floor underneath all the numbers. The second condition proves that W is the highest possible floor. If you increase the variable W by even a tiny amount epsilon, it physically breaks the floor. The new value is too high to be a lower bound, trapping at least one number X below it. This guarantees that the floor cannot be raised even a microscopic amount, perfectly defining the greatest lower bound. Before we look at a concrete example, we need to address a very common point of confusion. Students often confuse the supremum with the maximum, which is simply the largest number physically present in a set. Similarly, they confuse the infimum with the minimum, the smallest number in a set. There is a strict general rule linking them together. The supremum of a set is exactly equal to its maximum if and only if the maximum actually exists and belongs to the set. The supremum and infimum are boundary markers. They do not actually have to belong to the set itself, whereas a maximum or minimum absolutely must be inside the set. This brings us to a very practical formula that saves us a lot of time when analyzing simple collections of numbers. The supremum of a set S is equal to the maximum of set S, provided the maximum exists. If the maximum exists, the supremum locks onto it perfectly. If the set grows to include larger numbers, both the maximum and supremum increase together. For example, if a set contains the numbers 1 through 5, the number 5 is inside the set, so it is both the maximum and the supremum. However, if a set contains all numbers strictly less than 5, you can always get closer to 5 without reaching it. In this case, the supremum is still 5, but the maximum does not exist. Let us visualize everything we have discussed so far on a number line. Look at the blue line segment representing our set S. Notice how the red arrows for the upper bounds stretch infinitely to the right. You can pick any point there and it is an upper bound. But the supremum, marked by the green arrow at point B, is the very first point that touches the set. It is the tightest ceiling. Similarly, the lower bounds stretch infinitely to the left, but the infimum, marked at point A, is the very last point before the set begins. This visual intuition is exactly what our mathematical formulas describe. The supremum and infimum safely trap the set. Now that we have our formulas and visual intuition, let us apply them to a concrete example. We are given a simple finite set S containing the numbers 2, 4, 6, 8, and 10. We are asked to find the supremum, infimum, maximum, and minimum. Since this is a finite collection, we can simply look at the elements to find the largest and smallest values. The largest number physically present inside the set is 10. Because this number is an upper bound and is actually a member of the set, it serves as our tightest possible ceiling. Following our general rule, since the maximum exists and is inside the set, the supremum is exactly equal to the maximum, which is 10. Continuing with the same set, we now look for the floor. The smallest number physically present inside the set is 2. This acts as a solid floor underneath all the other numbers in our collection. Just like with the maximum, we find this simply by looking at the available numbers. Because the minimum exists and belongs to the set, the infimum is exactly equal to the minimum. You cannot raise the floor higher than 2 without missing the number 2 itself. Therefore, our final answer for the greatest lower bound or infimum is 2. This perfectly demonstrates how finite sets behave, where the boundaries are simply the largest and smallest numbers in the list. Let us move to a more complex example, an infinite set with no maximum. We want to find the supremum and infimum of the set containing all numbers of the form 1 minus 1 over n, where n is any positive integer. First, we write out the first few terms by plugging in n equals 1, then 2, and so on. We get 0, 1/2, 2/3, 3/4, and it continues forever. The smallest number in this entire list is 0, which happens right at the start. Since 0 is actually inside the set, it is the minimum. Because the minimum exists, the infimum is exactly equal to 0. Any floor higher than 0 would fail to support the very first number. Now we must find the supremum for this infinite sequence. As n becomes infinitely large, the fraction 1 over n shrinks towards 0, meaning the overall value gets closer and closer to 1. However, because 1 over n is always strictly positive, the result will always be strictly less than 1. The number 1 is never actually reached by any term in the sequence. It acts as an invisible barrier. Even though the number 1 is never inside the set, it is the tightest possible ceiling. If you pick any number smaller than 1, eventually the sequence will surpass it and break through your ceiling. Therefore, the supremum is 1, but this set has no maximum. Now that we have successfully used these formulas to find boundaries, a very important question arises. Can a single set have more than one supremum? We will prove that the answer is no. The supremum is absolutely unique. We start our proof by imagining the opposite. Let us assume that a set S has two different suprema, which we will call U1 and U2. If U1 is the least upper bound and U2 is just another upper bound, then by the very definition of the word least, the least upper bound must be smaller than or equal to any other upper bound. This gives us our first mathematical step. U1 must be less than or equal to U2. Continuing our proof, we must remember that we also assumed u2 is a supremum. This means u2 is a least upper bound and u1 is an upper bound. Therefore, the exact same logic must apply in reverse. We swap their roles, which gives us a second inequality. u2 must also be less than or equal to u1. We now have a situation where two numbers are each smaller than or equal to the other. The only way for two numbers to be simultaneously less than or equal to each other is if they are exactly the same number. There is no other mathematical possibility. This final result proves that the tightest ceiling is unique. Every bounded set has exactly one supremum. We have covered a lot of ground today, so let us reinforce the most important ideas. First, the supremum is the lowest possible ceiling you can place over a set of numbers, while the infimum is the highest possible floor you can place underneath them. Second, unlike a maximum or minimum, the supremum and infimum do not actually have to belong to the set itself, which allows us to bound infinite sequences that never quite reach their destination. Finally, these concepts are the ultimate boundary markers. Without them, the entire field of calculus would collapse because limits, derivatives, and integrals all rely on finding the tightest possible bounds. You have now mastered the first major step toward understanding advanced mathematical analysis.